So we're starting on page 6 of your notes, and we're looking at the evidence for the migration of ions. So the evidence that in solution ions are mobile. And this is a practical you're going to see in class. So here I have my U-tube, and in the bottom of it I very carefully put copper chromate in hydrochloric acid. Now copper 2 chromate has 2 ions in it. It has a Cu2+ ion, and those are blue. But it also has chromate ions, CrO4 2-, and those are yellow. Now when I put electricity across these, you will find that the chromate ions, the yellow ions, migrate to the positive side, and the copper ions migrate to the negative ions. So eventually what you're going to see is that this part of my U-tube becomes yellow as the chromate ions are attracted to the positive side, and this side becomes blue as they are attracted to the negative side. Now because we've also got some hydrochloric acid in there, you're going to see a few little bubbles around this end as the chloride ions are attracted to the positive electrode and become chlorine, and the hydrogen ions, the positive ions, are attracted to this negative electrode and become hydrogen gas. So you may see a little bit of bubbling there. But the interesting thing we're interested in is this colour change. So these chromate ions have migrated to the positive electrode because they're negatively charged, and the copper ions have migrated to the negative because they're positively charged, and that's why we see the colour change. Now in electrolysis, the positive electrode is called the anode and the negative is called the cathode. That isn't always that way round, but in electrolysis the positive is the anode and the negative is the cathode. So in this section of the notes we're going to look at the properties of the ionic compounds, and this is determined by the strength of the ionic bonding, which we talked about in the previous video. So there are two things we always need to consider. One is the size and the other is the charge of the ions, and those are what are going to determine the melting and the boiling points. Now in an ionic lattice there is strong electrostatic attraction, so a large amount of energy is needed to overcome that attraction and turn the ions from a lattice, a regular lattice, into a mobile liquid phase, which is why high melting points is one of the properties of ionic bonding. So we've got this strong electrostatic attraction between the oppositely charged ions, and that requires a large amount of energy to overcome. Now obviously the smaller the ion and the higher the charge, the stronger that electrostatic attraction is going to become and the more energy that's going to be required. So for example, magnesium oxide has a higher melting point than sodium chloride because of the size and the charge of the ions involved. The next property we're going to look at is the fact that ionic structures are hard and brittle. So this strong electrostatic attraction keeps the ion in this fixed lattice position. But if I hit it with enough force, I can get the layers to move. Now I only need to disrupt those layers a little bit to get now negatives opposite negatives and positive opposite positives, and at that point the crystal will shatter. So it's hard because it's got this regular arrangement of oppositely charged ions with strong electrostatic attraction. It's brittle because I only have to shift those ions slightly and then I get great repulsion here, and it tends then to shatter rather than bend. So you need to explain why they're hard, but unlike metals, they are also brittle. Having said that they have strong electrostatic attractions between the ions, you might then find it surprising that a large number of ionic compounds dissolve easily in water. Think about sodium chloride, which needs to be heated to over 1,000 degrees to get it to melt, and yet it will be soluble in water at room temperature. And that's because the water molecules are very polar, and they can form strong attractions, we call them hydration enthalpies, between the water molecules and the positively charged ions. And that is enough energy to overcome this strong electrostatic attraction. And you can see here the little water molecules attaching themselves to a negatively charged ion and then being able to pull it away from the lattice. So these water molecules are polar enough to what we call hydration enthalpies. They hydrate the ions, and that, because it's a bond forming process, releases energy. And that's enough energy to overcome this strong electrostatic attraction. We're going to study this in a lot more detail when we look at intermolecular forces and when we look at solubility. The last thing we're going to look at in this section is the fact that these ionic solids cannot conduct electricity, but when the ionic compound is molten or in solution, they can conduct electricity. And we need to understand the difference between the two. So, in the lattice, in the fixed lattice, the ions are fixed and cannot move. But when molten or aqueous, the ions are what we call mobile. They are free to move and therefore can conduct electricity. Notice we haven't talked about electrons. The electrons are not free to move. It is the ions, both positive and negative, which can flow and therefore conduct electricity. Whereas the solid, they're fixed in positions. They just vibrate around fixed positions. So that finishes this short video looking at the physical properties of ionic compounds. In the last section of the notes, we're going to be looking at the practical, looking at making ionic equations. So before then, you need to have practiced writing out full balanced equations, and in the next video, we're going to practice turning them into ionic equations. So until then, take care, stay safe, bye-bye.